Okay, I think I have it now. Okay, recording is in progress. So before I give the floor to Rob, I want to just say a few words about his background for those who know his name but doesn't know about other things. So if you allow me, I'm going to just read what I wrote earlier today. Professor Tibshirani is a professor of biomedical data science and statistics at Stanford. He got his that's an interesting thing because back in 1979, so nowadays everyone is a data scientist. Back in 1979, he got a BA, a Bachelor of Mathematics degree in statistics and computer science, which is everyone doing these days, from the University of Waterloo. And then he went to get a very clever guy, a master's degree in statistics at the University of Toronto. Did you ever overlap with Rob McCulloch there? No.
No, I didn't. I think he was after me.
Okay. And Rob's PhD advisor was Bradley Ephraim, famous statistician as well. Like everyone knows Ephraim from the bootstrap and other things. And two of his notable PhD students that I found on Wikipedia, and I know these people, are John Story, who does a lot of biomedical research in statistical biostatistics, who already has like 16 PhD students. And guess what? Larry Wasserman, which is a very famous statistician that I think he's the only Bayesian that became non-Bayesian over the years. And I couldn't, I have to tell that I like the research of another Tibshirani, Ryan, his son. I follow his career at the early beginning when he was in the job market. I was still a professor at Chicago, and he was stellar, got the job offers from everywhere. He's now associate professor at one of the strongest universities, like Carnegie Mellon Department of Statistics and Machine Learning as well. And Rob Tibshirani got like a number of fellowships. He's a fellow of the Institute of Mathematical Statistics, the American Statistical Association, the National Academy of Science is a member. And he got this COPS Award, President's Award, which is a JSM award for the most brilliant statistician before age of 40. He got it when he was exactly 40 in 1996. And just to finish, I list here a couple of his most famous books. The one that I like the most is the Generalized Additive Models and the Introduction to the Bootstrap. But also more recent, we have the Elements of Statistical Learning. Everyone uses nowadays the baby version of that one, the introduction to that. Just to finish, he has more than 380,000 citations for statistics. For people in this group who knows economists or people in economics, you can find a few people with that number, a high number, like James Heckman and a few other guys. But for statistics, 380,000 citations is like extremely high. Only the Lasso paper, the regression, shrinkage, and selection via the Lasso has 40,000 citations. So I think if you take all statisticians in Brazil combined, you don't have like that. And the 2005 book, The Elements of Statistical Learning, has 60,000 citations. So that gives you like an overview of the caliber of our speaker. And I'm very glad that you found the time to talk to a bunch of Brazilians again, because I've attended one of your talks like a year or two ago with the guys from Unicamp, which is another university in Brazil. So Rob, thank you very much.
Thank you. Thanks for the very kind introduction. I've actually never been to Brazil, unfortunately. I guess it's my second Zoom attendance. But someday I'd love to come physically. It'd be really, really nice. So let me share the screen. Let's see. Okay, can you see that okay?
Yes, I can see that okay.
So this is very new work, and I wasn't quite sure what to talk about, but I guess it's more fun for me to talk about my most recent work. If I were to talk straight through without interruptions, it'll only be about half an hour long. So I don't know, you can tell me whether you think this will work or not. If there are questions during the talk, I'm happy to take them. I know there's over 100 people signed up, so I'm not sure how feasible that is, but it's nicer, I think, if there's something that's really not clear, I'd rather you didn't spend the whole hour confused about something. So if there's something you're not clear on, see if you can ask it during the talk, and I think after the talk we'll have time for more questions as well. Is that right?
Okay, I will try to monitor whoever has questions in the chat room, but Julia, please go ahead.
So this is about cross-validation. Does it estimate, and how well does it do it? So it's kind of a narrow topic, but I think a really important topic, because cross-validation is something that's used, I think, by statisticians and data scientists. Anyone who's analyzing data, it's used very often. It's a central tool for supervised learning. And as we find this work, it's surprising how little we understand it, I think. And so this work is trying to contribute to our understanding of it, both in the theoretical sense and in a practical sense. Okay, and there's a paper, if you want to read up more, there's a paper here, an archive paper that's been there for about a month that describes the work in more detail, and you can look there. Okay. Okay, so my collaborators here are my long-term friend and collaborator, Trevor Hastings. We went to graduate school together at Stanford back in the 80s. And we've been great friends and collaborators ever since. And a tremendous student, Stephen Bates, who I said, thank you, Harvard, because he's another one of these students, undergraduates at Harvard, that our Harvard friends sent over to Stanford for PhDs, and it's very wonderful. Steve is an incredible student. He was an Immanuel Candace student, not mine, but I knew him well when he was a graduate student. And I was doing a postdoc at Berkeley with Michael Jordan. But of course, he's actually not at Berkeley at all. With COVID, he's still in Palo Alto, and that's been a silver lining to this pandemic, is that we could just see our students and former students more than we would have otherwise via Zooms. So, okay. So prediction, the accuracy of prediction, supervised learning is a topic here. And this is the foundational topic, right? And we're going to talk today exclusively pretty much about cross-validation, which has been around at least since the early 70s, and probably before, because it's such a very sort of obvious, intuitive idea that it's used a lot. Related to that is the bootstrap and other covariance penalties like CP statistic, AIC, BIC. Our paper talks about these methods in relationship to cross-validation in some detail. I'll have a little bit on the slide that I can give more information that people ask during the talk. And splitting up data, which is sort of
can everyone please mute the microphone? Sorry, Rob.
That's okay. So there's always related topics. We're going to focus almost primarily on cross-validation, but I'll say a little bit about these other topics and how they relate to cross-validation. Cross-validation, I looked it up on Google Scholar recently. It's got about 6 million search results. So this is a sign that it really is heavily used, and I think it's an important topic. So let's just review what it is, cross-validation. So we're doing some kind of supervised learning. We have some features, and we have a target, a response. That's our data. And we have a predictive model we fit to the data. For example, a lasso, a random forest, a neural network, whatever your favorite supervised learning method is. And we fit the model through an algorithm of some sort, right? And then we measure how well we do or how badly we do by a loss function, right? Which is the loss between the actual target and the predicted target. For example, for regression, that would most often be squared error, but for classification, it might be the 0, 1, for example, 0 if we get the classification, the class right, and 1 if it's wrong. And it works, cross-validation gives us an idea of the predictive error by the following idea. You divide the data up into k folds at random, k being, say, typically 5 or 10. And I've shown them here, 5 folds, k folds. And basically, it's like a k-act play. So in the first part of the play, you fit a model the first k minus 1 parts, and then you compute the errors when you predict the points left out in the kth part. Right? You do that in turn where each of the parts gets to play the role of the validation set. The other 4 parts, the other k minus 1 parts, get to play the role of the training set. So it's like a k-act play. And from this, you get these cross-validation errors, which are the errors for each data point I from a model that's fit on the other data, basically. Okay, so again, if this isn't clear, you should ask me now, because this is sort of the foundation for the whole talk. I'm going to assume that people know what cross-validation is because it's something we use all the time. Okay, don't be shy about asking questions. Okay, So here's, oh yeah, this is a more detailed. So and then at the next phase, so here we left out the kth part and fit on these k minus 1 parts. Here we leave out the k minus 1 part and fit on the other parts, etc. Right? So we do this k times, and at the end of all this, we get the CV errors for each observation, cross-validation errors. Important point being that the errors are each data point, the fits are done for each data point using data that does not include that data point. Right? That's the key point here. That's why cross-validation is so powerful. Okay. So great. So we get these individual errors. Now, what do we do with them? Well, typically we take their average, and that gives us the cross-validation estimate of prediction error, called it error hat. It's just the average of the errors. Good. And this is very powerful. This is very useful. I use this in my collaborative work. I use this all the time, right? This is a good point estimate. That's why I put a check mark here. A lot of this talk is I put this at the microscope here to see about what actually is this doing? Which error is it targeting? And that turns out to be somewhat of a quite subtle point, more of a sort of a theoretical point than a practical point, perhaps. But I'll talk about that. But first, I'll talk about the fact that the most practical point, which is that if you take the standard error of these numbers, so and this is what's done typically, you treat this average as a sum of independent things. You take the standard error and use this to form confidence intervals. So the question is this, can we take these at face value? Is this a good estimate of error? Is this a good estimate of standard error? Let me pause for a second. And as we'll see, the main point of the talk is that this standard error estimate is too small. And that's going to have severe consequences. Again, this is something that we didn't know. People have suspected for a long time, but we're quantifying it for the first time, I think, what exactly happens here. So what do I mean? So I'm actually going to start with the second issue, which is the most practical one. And then in the next part of the talk, the second part, I'll talk about the point estimate. The most practical issue we'll start with first, which is the standard error. Okay, so here in a nutshell is the problem. So here I've started with a model. This is simulated data with 90 samples of 1,000 features. And this is the case where we have a problem, when the number of features exceeds the number of samples. Whereas data these days very, very, very often have this characteristic, right? Because if you're in a medical setting, you might be measuring genes or proteins on individuals. Anyway, so it's quite common in medical settings and other areas where the number of features exceeds the number of samples. So in the simulation, the outcome is 0, 1. We've hit a lasso, a binomial model using cv.glimnet. This is our well-known package for fitting the lasso and elastic net to large data sets. And we set up to the Bayes error is about 20%. So the signal here is like fairly strong, right? Bayes error is 20%. So it's not 0, it's not 50, it's sort of in between. It's a moderate amount. Okay, here is the CV error that one gets from a realization.
You're in mute now.
It appears that you muted yourself.
Okay. Could you hear me before this? Not at all?
No, yes,
No,
it was my fault.
It was just for a few seconds.
Okay, good. Okay.
I muted everyone else because everyone is like entering and talking to other people. Sorry about that, but then I tried to unmute it, but I couldn't.
That's okay. So should I start? I'll start here again, or
yeah, right there. Everything to the last minute.
Okay, so again, estimating the standard error. So let me start this slide again. It's an important slide because it really shows the problem. Okay, so again, this is simulated data with 90 samples, 1,000 features. And again, the problem of standard error being off really happens when the number of samples is less than the number of features. And again, that's fairly common now, especially in medical settings where you can measure a lot of features on individuals, for example, genes, proteins, whatever you like. And the Bayes error was set up to be about 20%. This is a classification problem, two-class classification. Okay, so if you apply the cv.glimnet, you get this red curve as a function of the number of features selected by the lasso up here. So the most sparse models down here, there's one feature. As you move to the left, you get you get more and more features up to about 54. Okay, and you see the CV error is around 25%. which is not surprising given the Bayes error is about 20%. Okay, so but what does one do with this? Typically, you find the lowest point in the curve, which is about here, and then so the CV, the estimate of error is just here, this point here, and this looks like about 23%. But one also computes the standard deviation just from the standard deviation of those the n numbers here. Okay, the standard error, and we get the standard error of the mean is about 0.04. Okay, so if you form a confidence interval of target coverage on 90%, you'll get this interval, 16% to 32%. Question is, does this actually have 90% coverage? Now, we've had this BlimNet program around for many, many years, and lots of people use it, and people use other software. People form these kinds of confidence intervals all the time. They haven't really asked the question, it doesn't have the right coverage. I mean, if you put down a confidence interval, you expect it to have the right coverage, approximately, right? Turns out it's way off. And I want to give credit to Frank Harrell, who he gave a general talk at Stanford in 2019, just it's sort of a downer talk about machine learning. I mean, I like Frank very much, but he's very traditional and more of a, very practical statistician. He kind of was very doubtful about machine learning in general. All these people are saying, well, they're fitting models to huge data sets and getting great results. And we listened to him. We thought, I wonder if he has a point here. And he actually did have a point. And here is part of the point, that the coverage of this interval, which is supposed to be 0.9, is actually way off. How far off is it? Well, here is, I can move this. Okay. Whoops, didn't mean to do that. Okay. So here's a simulation from this same setting. Again, here's the CV estimate of error. Here's the standard deviation. Here's the confidence interval. The actual coverage that we want, the missed coverage we want to be 10% is actually 30%, right? So the coverage, which is supposed to be 90, is actually about 70, right? So here you see, here's the width of the interval. This is a bunch of realizations where we plot them against the true prediction error, okay? And you can see that the CI endpoint, confidence interval endpoints, the green guys are what we get from the formula, but they should be expanded to the red guys. Okay? So they're way too small. Now, who cares? Well, the first thing I do when I look at a classification and cross-validation error, I said, does the confidence interval contain 50%, right? If it does contain 50%, then it's saying there may be no signal in your data at all, right? If you can't do any better than a coin toss, then maybe your model is not useful, right? So that's the most basic sanity check for any model. Well, we don't have an interval that gives us a good idea of that, right? It's way off when p is bigger than n. So this, people had suspected these perhaps, but it's, at least to me, it was really quite eye-opening to see this, because we've been providing these confidence intervals all that, for years, and never actually asked the question, are they doing what they think they're doing? So let me pause for any questions, because this is sort of the central, I'd say the most central point of the whole talk. So when the talk, I'm going to show a way to fix the intervals to give them the correct coverage. And it's quite, as you can expect, you need to do a lot more computation.
I have a question, because earlier today I was reading, the first session of your paper, and this example was one that I was trying to understand. And one thing is, I noticed that these red intervals they are not necessarily symmetric relative to the green ones, but more importantly, do you think, are you going to explain at some point the size of this difference as a function of the number of regressors, or the sparsity, or is something that we never know? I mean, I'm sure that's probably the answer, but you have any feelings?
Well, first of all, the problem occurs when p gets really big, number of features. So, if I made this number of features 10 or something, there's no problem. Then the red and the green. So here's the main culprit is large p compared to n, right? Sparsity, I'm honestly not sure how it plays a role. I mean, yeah, I would guess the more sparse the model, the less of a problem this is. Oops, sorry, but how do I do that? Sorry, somehow got back to the, yeah, so I'm not sure how sparsity plays a role, but the main point is that the number of features make it worse. As the features get large, number of features gets larger, that makes it worse. Okay.
Thank you.
Okay, so why does the problem occur? Well, it's really sample reuse. If you think about it, kind of obvious in retrospect, right? That when you do cross-validation, every sample gets to be, let's say it's 5-fold cross-validation. Every sample is used 5 times, right? 4 of the times it's in the training set, and then 1/5 the time it's in the, or 1 time it's in the validation set. So it's reused, and this reuse causes a positive dependence or correlation between the errors, making the variance too small, right? If you have a sum, if you have a mean, and you want to know the variance of the mean, right? Then the usual formula we use assumes they're independent, the things that are being summed. But if they have positive dependence, that variance is actually larger than you think it is. That's the problem. So here we quantify it in some detail, more in the paper, but here's 5-fold cross-validation. The red indicates that the dependence of observations in the same fold, and the blue indicates the dependence of observations in different folds. And if you do like a variance expansion, then you can see that the form that we typically use is just the first term, which assumes that they're independent, but there's additional terms which are caused by the dependence of observations within a fold and between folds. Okay, so the typical form we're using is just this leading term, but the actual variance can be, it is, as you see, much larger because of the dependence. Okay. Okay. So here's, let's say, the most important slide of the whole talk. In terms of, this is sort of the, move this again. You guys are seeing this, right? I can't get out of the way here. Okay, that's good. So I'd say this is the most important slide from a practical point of view. It's like the one sort of secret sauce that we're offering in the talk. So this is how we're going to fix the problem. So here's k-folds again. And we're going to basically do a CV within a CV. Okay, so it's, let's say it's k is 10. We're going to do 9-fold CV here, and then have the 10th point left out. So it's going to be a CV within a CV. But here's how it proceeds. Well, first of all, it's all based on this identity. So let me tell you what all these things are. So here is the CV estimate of error for, I say in because it's in. So if I have 10 folds, I'm going to start by doing 9 folds CV on the first 9 parts, and just read off the error, and that's going to be error in because it's in the sample. Okay. Error XY is the target error. It's the error that we're trying to estimate. So this is the variance. Well, this is the mean square error of the CV estimate. And if we're taking a square root, it's basically the standard deviation of this quantity. If there's bias, it'll just make these things conservative. So this is what we'd like to get, right? This left-hand side. We're going to get it through this identity. Okay, this identity is very simple to prove. It's just basically Pythagorean theorem. But we're going to, the next slide, I'll go through this in detail. We're going to actually use a CV within a CV to get this quantity and this quantity. The key point being that it only involves the expectation. It doesn't involve any variances. As soon as you take a variance of a sum, you have a problem with the correlations, right? That's what we saw in the previous slide. This only involves the expectation of quantities. If you can get an unbiased estimate of this quantity and this quantity, then you're all done, right? Because then you just piece them together to give you the left-hand side. So we want this. We're going to use CV within a CV to get this quantity and this quantity. Okay, now I haven't explained how we do that yet. Well, I've almost explained it, but let me actually walk you through it step by step. Whoops. Just trying to. Okay, so here it is. This is the same identity. There it is. So here are the steps. So we divide the data into k folds, say 10. On the first k minus 1 folds, just basically run, if you're running glimnet, just run cv.glimnet or your favorite supervised learning with cross-validation, k minus 1 fold cross-validation, and just read off the error estimate you get. Okay, that's good. But you also, we have the kth fold that we've left out. We'll compute the e bar out. That's the error on the holdout fold. So you've got this 9 folds over here, and then you have a 10th fold you've withheld. You're going to compute the CV error, on the first 9 folds, and then you're also going to compute the error it gets, that model gets on the remaining fold. Okay, and that gives you one realization of this quantity because we got error bar in and I got error bar out, right? So it's, and we expect basically, we normally expect this to be larger than this, but it's whatever it is, here it is. We get one realization of this. We also compute the the variance of the errors in the left out fold, the empirical variance of the errors. Okay, and that's just this, right? Remember that fold has maybe 20 observations. Its error is just an average of them. We take the variance of the average. This gives one estimate of B, right? Because this is just the variance of E bar out. There's this expectation, and there it is. So just from this 9 folds and a holdout fold, we get one of these, and that's it. And now this whole thing is repeated over K going from, little k going from 1 to K, and then we also take more than one choice of the K folds. But all we're getting is this quantity, one realization, and this quantity. Do this many times and take their average, and that does it. So again, this is actually quite subtle, because again, the reason this works is that it only involves expectations. We try a lot of other things, but we're foiled by the fact that as soon as you get introduced a variance, you have to know the correlations, which you don't know. This in a very simple way, using CV within CV, gives you the things you need. So at the end of the day, you get basically this quantity, you take its square root, and that's your standard deviation. So the next slide actually goes through it again, and then I'll stop it goes through it now with pictures, same idea, and then I'll stop for questions. Because again, this is sort of, I'd say, the one main idea from a practical point of view in the paper. Here we go, here's our K folds. This one's the holdout. We do K minus 1 CV in the inner part. We fit the model here. We get these individual errors on the holdout part. We do it, so I'm playing CV inside the inner part. And I do this looping through 1 through K minus 1. I get these errors for each one. And again, I get what I saw on the previous slide. I get this term and this term, and I simply average them over 1 through K minus 1 plus random split. So I do the K folds many times, right? I do one K fold. I choose one set of K folds. I do K minus 1 CV within the first K minus 1. I get the holdout, and then I get another choice of K folds. Do this many times. Again, I'm just taking an average. It's just like a Monte Carlo estimate of expectation, and that's it. So let me pause for questions. I mean, the hope is that if you've seen this, you think about how you might code this up in R or Python or something, because it's not difficult, right? It's just, you just have to call your supervised learner many times. That's it, and compute errors.
So there is a question here by Guido. He asks, do these biases depend on K?
Biases depend on K. Not very much, no. And there's a section of the paper where we look at like leave one out cross validation, 5-fold, 10-fold. Doesn't seem to make much difference. Yeah, I mean, there's been a feeling that like leave one out cross validation is somehow bad or something. It's not true. It just the only downside is it takes more computation, but the performance isn't affected much by the choice of K.
I have a question. So the way you do it, the IK can be bigger or smaller?
IK can be bigger or smaller. Which was, these guys here?
I mean, in terms of the size of the holdout, it should be like, is there any benefit of making it larger or smaller than the other ones?
I see. So, I mean, by default here, I'm saying if N is 100 and K is 10, then I simply take each IK to have 10 observations. But you're asking whether it would help to make the blue part bigger. Not really, because this is all very symmetric. Well, let's see. Okay. It would make a difference. I don't know what direction it would go, right? Because it's sort of no free lunch here, right? You make this bigger, so you have more test data, more holdout data, but they have smaller training sets. So I'm not. It's a good question. I don't know. We've just kept them the same size, but it would make a difference. But it's going to be, it's going to be good or bad. It's going to make your training set bigger or smaller, and correspondingly your holdout set bigger or smaller. So, right?
Yeah, because when you do cross validation in general, like the K-fold, you essentially divide the groups in roughly the same size. You don't have to, but you do it.
Right.
But
yes.
Now that you have this additional set,
yes.
I mean, it would be nice. I mean, I'm actually curious. I'm probably going to run something small later on after the talk. If you make this half the sample size or 1/3 or 1/4, something that is not necessarily a function of the k-1 fold.
It's interesting. My guess is that you're better off having them all the same size, but I could be wrong. Yeah.
Thank you.
Other questions? Okay, so this, we don't have
Sorry,
theory.
there is one more question. I'm looking here at the chat. Pedro Luiz is asking, is this idea applicable to structured data like stratified PPS samples or time series, I would add?
Yeah, that's a good question. We started to think about that. Like if data is time ordered, then you of course don't want to do cross validation. You want to do some kind of forward ahead validation, right? You always want to be predicting the future from the past. So we started to think about that. I think it's applicable. We haven't worked out the details yet. And PPS is that what's that standard? Stratified proportional to population proportional sampling. Again, we haven't looked at it. I suspect that with modification this would work, but we haven't tried that. I mean, the basic problem is whenever you do cross validation, you're going to have this positive correlation you have to deal with, and it's probably going to happen whenever, even if you have stratified sampling, and that's not going to fix that problem, right? It's just going to change it somehow.
One
Yes.
Quick question. Would the estimate for the average of the error be the same of the non-nested cross-validation? Like, because now you have two estimates that you could make. You could average the error in, or you could average the error out. So
I think what you're asking is right. So what we're doing is we use the error from all k folds, which is the usual error. But you're right. You're saying one could use the average of these error ins over the k-1 folds. It'd be similar, right? But
okay,
we use the standard estimate, which is just the average over all k. The error derived from all k.
Okay, thank you.
You're welcome. So just to say, we don't have solved theory to say that this is always going to work. It's complicated, right, with cross-validation, but we have, the derivation is very reasonable, and in quite broad simulations in the paper, it does work in regression, in classification, high dimensions, low dimensions, sparsity. So here's an example, that same example, where now we get, again, the usual CV was way off. Its miscoverage was like 30%. And now we're getting close. I mean, 6%, 7%. And in other examples in the paper, see, sometimes it's a bit low, a bit high, but it's really on the average quite reasonable. And this, one doesn't have to do any kind of tinkering. It just works. So here's the nested cross validation. You can see it gives us the blue ones. So again, the naive ones are green, they're too narrow. The actual quantiles in the population are the red, and the blue. The blue is a little not wide enough here, and a little too wide here, and on the average, it's about pretty close to right. Okay, so that's the end of the first part, which is talking about the problem with confidence intervals and how to fix them. So just to recap, the basic problem occurred because the samples are reused, giving you positive dependence, making the standard error estimate too small. Again, it really happens when p is bigger than n. But this can be really, it's not a little problem, it's a big problem. It's quite a severe thing, which surprised us as well. And then this new procedure we've introduced seems to be able to fix it. What's the drawback? It takes a lot more computation, about 100 times more computation than usual cross-validation. But I don't tend to worry about computation, right? I mean, for example, this can be parallelized on my MacBook Pro. This example we just saw takes just about 1 minute in a, I'm not a specialized computer. And our friends in computer science will always come up with smarter algorithms, software, and hardware to make things faster. So I don't think this is really a limitation. It's going to be a limitation if you have very large data sets, but for sort of things which are moderate size is not even currently a problem. Do you need to do this? Well, again, the situation is worse when the number of features is a much larger number of samples. And it seems like the more that you regularize So someone asked us earlier about sparsity. The more you regularize, the less the problem is too, although it's still quite substantial. So most of the theory of the papers we'll see talks about least squares where there's no regularization. But I think an interesting area to think about is how when you have an L1 or L2 penalty, how does it sort of affect the sort of qualitative results you'll see? And we have software in R, which is online. If you look in the paper, there's a reference to Stephen's GitHub repo, and we have software there if you want to try it. And eventually there'll be a new function in GlimNet which does this. So you'll run GlimNet, you might run CV GlimNet, and now if you sort of finalize your model, you want to get the confidence intervals more accurately, you can run this additional function, maybe called ci.GlimNet for confidence intervals, and it'll do all this for you automatically. Again, it'll take more time than usual, but hopefully that'll be not a problem.
No, that's not a problem.
Okay, so any questions about this before I move on to the next part, which is sort of more foundational and fundamental about what is CV doing?
Someone asked a question, I think is related, not necessarily direct to this point, but it's related. He says, since random forests randomly selects a group of parameters at each split, would this CV problem caused by a larger P still be relevant?
Well, okay, so that's a good question. So I have a student working on random forests, and this, first of all, CV is not really the method of choice for random forests. I mean, as the question already asked, random forests, they already do sampling. Well, it turns out you can use the existing samples of random forest to do this kind of correction. It's not CV anymore, it's like a bootstrap. It's a bootstrap, of course. But so this problem occurs for bootstrap, is an analogous problem, and you can fix it, it looks like, too. But that's sort of work in progress. But so yeah, for random forest, it's going to be actually easier because you've already sampled in a random forest. So you can just reuse the existing trees you've sampled with the right sort of arrangement, and you can get a good estimate of standard deviation. So I have a student again working on that, and hopefully within a month or so, we might have a paper out on archive. Happy to give more details. Okay. So this was sort of the first part, but I mean, first of the 2 points. What is cross-validation? The estimate of cross-validation, just what is it doing? Some people might think, well, who cares? Okay, well, at some level you don't care, but at a more, I think, more foundational level, it is pretty interesting, and maybe it has some practical consequences. So here's what we're talking about. And this, oops, this can get a bit confusing. So, okay. I had this before, this error XY. What is this error XY? This is like this is the test error of my model with my trained data. So my trained data is X and Y. That's the notation here. And this is saying error XY is the error I expected. This is the actual prediction error, test error, conditional on my XY. So you have a training set, you fit a model to it. What you'd like to know is, for my model on my training set, what is the error I expect to see in a new population? Right? That's what we call the error XY. This is what we'd like to think cross-validation is doing, right? That sounds ideal, right? You've got your data, you have your model, and your collaborator says, well, that's great now. What error can I expect if I use that model on my future data, right? Somehow the trained data is going to be fixed now because it's your trained data. So this is what we'd like to think we're getting with cross-validation. As we'll see, we don't get this. What we get more is an average error. So here's the average error. It's the expectation of this conditional error over training sets. So this is the error now. If I think of the error for my given training set, my given model, and if I average this over choices of training sets, this is the average error. Again, so what's being averaged here? Well, the test point is always being averaged. There it is. Here's the test point. We're also averaging over the training sets here, right? X and Y. And in a lot of work on error, like in Brad Efron's work, this is the error he talks about. Well, he talks about the in-sample version, but this is the kind of error one normally talks about. Well, so the question is, does CV, the first question is we'd like to think that CV gives us an idea of this conditional error. Is it the case? Well, here's a little simulation where we've plotted, each one's a realization from a data set where I fit a model. This is the CV estimate versus the conditional error. It's got basically no correlation. Well, look at it, right? I mean, there's no correlation. So in other words, it seems that cross-validation cannot tell you about the error conditional on XY. Of course, on the average, it can give you a good idea of the error. That doesn't mean it's useless, but it says the deviations of this around its mean are not predicted by CV estimate. There's no correlation, basically. Okay. This is, let me drill down more into this point. This is, I think, an interesting way to look at it. So if we make the model more specific, we can actually say something more definite. So now if the model is linear with normal errors, okay, then this is an interesting statement. This is the more official statement that conditional on X, error hat CV is independent of error XY. And again, here's another picture. Here's a picture I get out from this model. Here's error XY, and there's no correlation. Correlation is 0. And you can show theoretically, there's actually a simple proof of this in the paper that conditional on X. So given your training features, error CV has no information about the particular Y that you see the target. Because it's independent of error XY given X. So what's the consequence of that? This is like a little sort of thought experiment. Suppose Trevor has some data and he wants to get an idea of the conditional error for his model. Okay, and he computes cross-validation. Rob also has some data. It's very similar to Trevor. It's got the same X's, but the Y's are fresh Y's from the same joint distribution of XY that gave Trevor's data, right? Well, we show in the paper that the consequence of this is that Rob's estimate is just as good for Trevor's test error as his is. In other words, if Trevor wants to get an idea of the test error, there's no reason to prefer his data to Rob's data. It's interesting, right? They have the same joint distribution. So from a statistical point of view, there's no advantage of using, for Trevor to use his actual Y's as opposed to a fresh set of Y's with the same joint distribution. Just another way of saying that given X, there's no information in the particular set of Y's that Trevor saw. Right? He might have seen a good set of Y's that was good for prediction or a bad set. Cross-validation can tell you nothing about that. And maybe it's not surprising, right? Because you're asking a lot for cross-validation. You give it a training sample, and then it just reuses it in many ways. Perhaps it's not surprising that it can't tell you much about your actual sample, right? Because it's having to reuse your sample just to get the errors. So let me pause on a second for this on this slide. And the main sort of theoretical result is in a linear model of normal errors, conditional on X, error hat CV is independent of error XY. So the main consequence of all this is, although we'd like to think that error XY is our target, right? We can't get it from cross-validation. And it turns out, as I'll show on the next slide, you can't get it from any other method that we know about, bootstrap or AIC or anything else. Well, I'll show that, but we started with cross-validation. So let me let you try to ponder this slide and then. Okay.
And in this example, you don't even have the pathology of the previous one, right? You have more data than features.
Right. Yeah.
So
there's nothing here. Right. This has nothing to do with doesn't require a large P rating. Right. Your P is just 20.
So if I look at this slide at face value, anything I hear from now on about people doing like k-fold cross-validation, which I already thought was half of that was garbage, is now 100% garbage.
No. That's I don't want to give that impression. A CV is extremely
That's why
useful.
I said.
Okay, no, I don't want to give that impression. And I gave a talk. This is the second time I've given this talk. Someone else asked that in the audience. They said, "Does this mean we shouldn't use cross-validation anymore in our daily work?" I said, "No, use cross-validation." But this talk is making 2 points. The standard deviations are not correct that you're getting, and there's a better way to get standard deviations. The second point is that CV is not doing what you think it's doing, but it's still useful. It gives you a good idea of error of this. It gives you a good estimate of error, which is fine, which is something useful, right? It's the average error of your model, but it doesn't give you a good idea of error X. Whoops. Why does this keep happening? It doesn't give you an idea of this conditional error, but it's certainly it's too much to ask in the first place, right? Because all you have is your training data, and now you're telling me, you want me to, using just that data, we want an idea of the error conditional on that training data. Well, that makes it very difficult. So it's maybe not surprising. Yeah.
So a related question. So how would you rename the conclusion then? If you still use cross-validation, and instead of saying, well, this is the error rate of my model, but you, in the previous slide, you basically said, well, you're actually doing an average.
Average, right?
So how can you rephrase that for the general public? Like you say, oh, it's not this, but it's that I'm computing.
It's the
They might,
average
they might still be happy with that, right?
Yeah, it's the average error of my model, right? So you have your model and you have your data, you fit a model, and you tell your collaborator on, and the average error rate is 14%. That means, if I were to get new samples of data from this population, this training set, and apply my algorithm each one, on average, I get an error of 14%. I can't say for this particular training set, this particular model, it's 14%. It's an average statement. So that's all. Right?
Thanks.
Yeah. But again, if just conceptually, this is the other sort of important slide. So, and I don't have a lot else to say. So if you have questions about this, please don't hesitate.
There is another question here from Paulo. I don't know which Paulo is that. Does this nested CV method reduces error bias if instead of MSC, we use rank-based metrics such as Gini, ROC, AUC?
I'm not sure I understand the question, but I will say that, so here I've just focused on squared error or misclassification rate, but if my error measures like AUC or something like this, I happen to have the same problem, and I think the same method can be used to fix it. So, right, again, the positive correlation is going to cause problems in the standard deviation of the AUC, for example. Same thing's going to occur. The question seemed to suggest maybe it's not going to it's going to solve the problem. I mean, I don't think so. I think, well, maybe the fact it's rank based might make it a little bit better, but I think in general, you're going to have a problem, and I think we have a way to fix it, basically. So if you use AUC or whatever your favorite error measure, you're going to have the correlations are going to cause problems, and you can fix them.
Thank you. I guess that's the loss function that you talked about at the beginning of your paper, right?
Well, not the loss function. It's let's go back to that. It's the error measure here. Did I say we're way back at the beginning here? So it's, I beg your pardon. Yeah, it is the loss function. Yes, right. So there's an objective function that's used by the fitting algorithm, but yeah, it's a loss function. You're right. So if it's AUC, which is a very good thing to use for classification, there's survival analysis versus AUC. You're still going to have the same kind of problem, the same challenge, basically. And although we haven't worked out the details, I believe that with the same scheme can be used to fix it. Okay, so almost done here. So we talked about this, and then here we assume that a true linear model with normal errors. You can go a little further. If you don't assume normality, you can show that this correlation goes to 0 as n and p go to infinity. And along the way, we showed that basically the true target of cross-validation is either the average error or this error x, which is what we condition just on x. These are about equal, and they're much smaller than this error, right? So here's an example. Down here, we've got the 3 targets of inference: the overall average error, the average error conditional on x, and the average error conditional on, and the error conditional on x and y. See, these are very similar, and this guy is much bigger, right? But we can't really get an idea of this because the estimate of CV has no correlation with this quantity. In other words, this guy varies around error x, but its deviations have no correlation with cross-validation. We can't get any idea of whether your particular y is good or bad. We can make an average statement about your procedure. And then this is kind of near the last slide. So this lack of correlation comes from the fact, well, it's true if this property holds for the error estimator. So for example, for cross-validation, if you add kappa times x1 through kin to the target, and if this doesn't change the error estimate, then we call this linearly invariant. This is true of cross-validation. And it's obvious because you're just doing cross-validation with least squares. You're doing least squares regression, you're cross-validating. This is true of cross-validation. It's also true of bootstrap, Mallow CP, AIC, RCP, data splitting. And as a consequence, the lack of correlation between AirXY and the estimator also holds. So for all these things, all of them give you an idea of the average error, not the conditional error. Okay. We also compared this new procedure, the nested CV, against data splitting, and it does quite a bit better. Data splitting is very nice because it's simple. So what do I mean by data splitting? It means you take your data, you divide it, say, into 2/3, 1/3. You fit your data on 2/3, your model, and you assess it on the left out third. That's it. Well, that's pretty good. The problem with that, I mean, it's unbiased. The problem is that you lose a lot of power by cutting your sample size down by 1/3, right? Cross-validation does that, but it reuses the data so that you don't lose its power. So we show in the paper also the data splitting is kind of reasonable, but again, when P is large compared to N, you lose a huge amount of power, which is just not worthwhile. So there's more discussion in the paper about the other methods, how they relate and compare. But the main point for the talk is to say that this lack of correlation holds if I replace CV by whatever you want, bootstrap, AIC, CP, RCP, data splitting, it's all, and then the proofs are simple. Okay, and I think that is about it. So as a summary slide, I talked about two things to do with cross-validation, the confidence intervals, which we show that the naive intervals, which we all use now, can be much too small because of this positive correlation. And this typically happens when P is larger than N. And this new procedure we've introduced seems to be able to fix it by doing with a CV within a CV. And then the second part was about what exactly is cross-validation targeting. And the conclusion is it's targeting the average error, not the conditional error. And we're working on, I mentioned this already, some extensions to all this is survival analysis, other prediction measures, etc. And I want to thank Frank Harrell, who again, his talk really motivated this whole work. In 2019, Brad Efron, who's my supervisor and friend, who's really done tremendous work on this whole area since about 1980, and he's responsible for most of the great work in, I think, in cross-validation. Of course, bootstrap invented it. So, and Brad's, we talked about Brad about his work. He's it's very interesting. Of course, he thinks it's too much computing, but he's very interested in this and happy that we're doing it. So that's it, and happy to take more questions or suggestions.
Okay. So are there any questions specific? You can open your mic or you can raise your hand, because I think that's an option here. If not,
just a quick one.
Identify yourself and
yeah, my name is Paulo. Just a quick one. Thank you very much, Professor Tibshirani, for the seminar. Just to confirm one thing, when you say that CV is estimating the average prediction error, there is a connection between this statement and the proof in the paper in your first slide by Stone in 1977, right? Because there he proved that the cross-validation error converges almost surely to what you're calling the average prediction error.
Right.
Is that correct?
Yes.
Okay. Thank you.
Thanks.
so Guido is asking another question. Can you ask Guido? Are you there?
Yeah, sure. I think I have a little bit of background noise, but I can try. I'm still digesting the second part, about the what CV estimates. I think I still have to sleep on it, but to help me, could you expand on how this CV estimate relates with a potentially true relation between X and Y? Because you see, you're saying that we're estimating an average relationship, yes. But if there is such a thing as a true relationship between X and Y, does CV relate to it in any way?
Well, of course, there always is a true relationship. I mean, it's a philosophical question, but CV relate to it? Well, I mean, we're just saying that the expectation of CV is approximately this average error rate, which is the average error rate of the true model, which we don't know, of course, but so there's a true model either in simulation or in real life. We don't know what it is. We get data from that model. We fit our supervised learner. We do CV, and the expectation of CV on the average is that true error of this unknown model. So I hope I've answered your question. So that, yeah, it does relate. Its expectation is the error of this true unknown model, which is why we use CV in the first place, right? We think it's telling us something about the true underlying model.
Yeah, if I can follow up.
Wait, I have two more questions from other people, and then you follow up after that because we have limited time. Matthews want to ask a question. Can you go ahead, Matthew? Mateus?
It was not mine. It was someone asked at the beginning. The question
you asked the question for me, so go ahead.
It was about tuning hyperparameters. So the original question is, if you choose the tuning parameter of lasso using CV, does it make the conversion worse? And by that I mean the conversion of the original CV.
Yeah, that's a good question. So I kind of brushed over that. So maybe one way to say the question is that, the analysis we do in the paper assumes that the lasso parameter, like here, the log of the lambda, is fixed. Like, and typically what you do is what we did here is we take the minimum of the curve and we say that's lambda hat, and then we fix it, in this confidence interval construction. But you bring up the question, well, of course, lambda hat is not known. It's estimated from the data. So how does that figure into things? And it's a good question. I don't know how it affects things both mathematically or practically, because it's going to induce another source of variation. And even beyond that, like you often have other hyperparameters, right? Like if you're doing a random forest, you might pick the number of trees or how deep each tree is. How does that figure into this, this procedure? So the answer is I don't know yet, basically. But in the paper, we've made the simplifying assumption that we choose lambda hat and we fix it.
Cool, thanks.
Okay, so two more questions. I think the next one is Florencia Leonardo. Florencia, are you there?
I'm here. Thank you, Ediver. So my question is, in the confidence intervals, in the first part, I think you use the conditional expected error, right? The conditional on the sample. So these confidence intervals are still valid for the average error?
That's a good question. They are because, let's see. Yes, because if you cover the conditional error, you also will cover, you'll be conservative for covering the average error. And we have the simulation in the paper, we show coverage both for error XY and for error. And the coverage is both the same. And so that's a good question.
Okay.
Yeah.
Thank you.
Thank you. Anderson Ara has a question. Maybe he's not there anymore. Okay, so Clécio, are you
hear me?
Oh yeah, go ahead.
Okay, my mic is off. I'm sorry. The holdout validation is the repeated holdout validation is a very good estimative to predictor error. How we can extend these results to a repeat holdout validation for any model?
To extend the results to repeat holdout, I'm not sure what you're asking. I'm using repeat holdout cross validation. So I don't know what you mean by how can I extend it?
Yes, it's data splitting many times over. You can be the same sample in each step. So you can split as 70-30.
Yeah.
Data splitting many times.
Mm-hmm.
So you don't have a cross validation. In fact,
you see. Yeah.
We may extend these results to repeat holdout validation or not.
I think I understand what you're saying. Like I've assumed that this is the repeat holdup. Within the K-1, I do cross-validation. You're saying I could just do a single like 70-30 and just in here. And so this be 70, that'd be 30, and do that many times. That's, let's see. That would work as well. Well, is that true? Like, hey, we need to get from the inner part, we need to get some estimate of the error. So you're saying you could do 70-30, right? You could get the error. Yes, you get the error from the 70 and the error. Yeah, that would work. Would it be better or worse than this? Oh, but we need also have to get a variance of, yeah. In principle, that would work. Intuitively, I don't think it'd be as good because you're not using as much of the data. You're not like I'm using this K-1 times, but I think this all goes through for data splitting. Yeah.
Okay. Thank you.
I think you're muted.
Okay, sorry. There is one more by Clasio, and he said he has no mic, so I'm going to read what he wrote here. In my experiments using BIC to choose the best lambda, sometimes we don't have global minimum. What do you think about it?
This is for lambda for the lasso. What learning method are we talking about?
Probably the lasso in that picture. I'm not sure. I mean, he just wrote that.
Okay. Well, yeah, that can happen with cross validation. There's no guarantee that there's a, well, I mean, the function is concave or anything. So that can happen. Yeah. I don't know. There's no guarantees that you're going to get a unique global minimum. Yeah. But I don't really address that here. So.
So do we have any more questions? Well, I'm going to open this.
Should I unshare or okay?
I was just like opening my mic here because if you have any more questions.
Does he have a question?
Yeah, I was just like, you know, my son just came from school, and because he goes for school for 4 hours, I toss him in the shower because that's the norm these days because of COVID and all. But now he's here, like I'm have to clothe him, and he just took like some piece of candy. I said, oh, yeah, go eat your candy because you give me 5 minutes of peace.
Okay.
Well, if no one has any more questions, I want to close by thanking Rob Tibshirani again for spending his precious time sharing his most recent paper with us. You can find his paper, this paper, and many others in his website, which is very nice to find other things as well, like, you know, code for many of the methods that they propose. There is even a lasso webpage with a cowboy, you know, lassoing a cow. And if not, Sergio, you want to say anything else or?
I think
thank you again, Rob. It was a pleasure and a great honor to have you here. Thank you.
Well, thank you for inviting me. I think I've been asked whether I could be hanging around for more meetings or questions, and I can, for the next hour, I can do that. If there's people that still want to, you know, talk about anything, I can, if not, I'm happy to go back to work. So whatever people want to do. I think the organizer asked me or by email whether I could be available for more meetings. And I said, well, following the talk, I could hang around if there's interest.
Forward.
Hi. So my name is Cristiano. I work in a bank as a portfolio manager. I would like to know from your future work, what's going to be your future agenda? What have you been working on? What have you been researching on?
Oh, well, lots of interesting things. I do a lot of very applied work, mostly in the medical area. So that it often suggests things that tools that are needed. One thing I'm working on, well, just about to publish a paper, actually, a marriage between the lasso and neural networks. So it's a feature sparse neural network. You know, one of the challenges when you apply a neural network is it can predict very well, but then when you ask the question, well, how is it working? What features are important? It's often very difficult to say, right? And what people do now is they kind of do a post-mortem. They look at the fitted neural network to try to drop some features and see whether the predictions are affected much. But that's kind of too late because the model's already, it's not been encouraged to use fewer features. And what we do is we have basically a GlimNet style path, an entire path of models that are feature sparse. So at the one end, you have a usual neural network, multiple layers at every one. And then as you increase the sparsity parameter, just like in GlimNet or the Lasso, the network uses fewer and fewer features, right? And if you can, in many cases, you can do so and without much loss of prediction accuracy. So you might reduce the number of features down from 1,000 down to 50 or something, and the resulting network is much more useful, right? It's useful. It's more useful because you can understand what it's doing, and you also, it means that if you're going to use it, say in a medical setting, you don't need to measure 1,000 things. You need to measure 50 things, right? And if those measurements are expensive, like the protein measurements or gene expression measurements, you'd much rather have to measure only 50 rather than 1,000. So I can point you to I guess that's one of the big things I'm working on recently. We're just about to publish this. In arXiv, there's I'll just share the screen for a second to show that paper. Okay. So here, this is the paper that's about to appear in JMLR. So it's a neural network with feature sparsity.
Very interesting. Thank you very much.
You're welcome. Are there other questions or suggestions?
Well, I mean, I'm going to abuse a little bit of your time and ask you for like an overall view of, because I see here that you are in biomedical data science apart from statistics as well. So data science is a new thing these days in many areas. Sometimes it comes through engineering schools, sometimes from business schools, other times from medical schools. Like so can you share with me and Sergio, because we are, organizing a bunch of things here at school on data science, how you see it, what are the connections with other schools in the university, or what kind of people are being hired these days in your younger, generation of data scientists / statisticians?
Right. So, I mean, we tend to, well, of course, the last few years has been pretty much a hiring freeze, but we tend to be hiring some traditional applied statisticians, but also now more people who are much more computational, do machine learning. They worry about privacy, fairness of algorithms. So there's kind of a mix between machine learning and statistics and CS, for example. So, I mean, this campus is also trying to figure out just how should data science evolve, basically, and we're not really sure yet. I mean, I guess the only thing that the thing that I kind of hang on to is as long as I'm useful to scientists. So, I think, to me, a real measure of whether you're doing the right thing is if your work is useful to scientists, right? So that's why I try to do a lot of work and collaborative work in the medical school, just to know what scientists are doing, the kind of data they're collecting, the kind of problems they're facing, and try to be useful to those people, basically. And whether that requires a linear regression model or a lasso or a random forest or a deep neural network, just try to solve scientific problems the best you can. And then you'll always be, you'll always have value, I guess, right? Because it's easy to sort of go off and do sort of theoretical things, make up problems that seem convenient, either theoretical. But to me, I guess I'm much more practical oriented. I try to help scientists solve their scientific problems. And if that leads one to sometimes to new areas or new things you need to do, that's great. But I try to always be sort of guided by what's useful to people. So that's sort of a vague answer, but.
Yeah, on a related, more focused point, where do you gather these people these days? Like, are these kind of profiles, are they already coming from stats department, or they're still mixed in stats, computer science, or other areas, or you don't have any?
They're coming, well, more and more statistics students do postdocs. And so they tend to come, and at the same time, people in machine learning will do postdocs. So they tend to come from either of those fields. And during postdocs, they'll learn about the other field. Like people in machine learning will learn about causal inference or more traditional statistical topics. People in statistics may learn more about algorithms and neural networks. So by the time they do a 2 or 3 year postdoc, they're pretty well equipped to do that kind of work. So yeah, there's so much more to learn now that one has to typically do a postdoc to catch up, I think, to broaden your expertise.
Yeah, this is something that has become very common in statistics, but in economics and other areas, they don't have this tradition. Starting right now, people doing postdocs, they are more infancy. So I think this is that's a good point that you brought up.
Yeah.
Thank you. Well, if you don't have any more questions, and if no one wants just to hang out, so I'm going to go and give lunch to my son.
Okay.
Thank you, Rob. And I hope I'm overstepping Sergio here, but inviting you to come to Insper as soon as you are able to travel, because I really wanted to have this in person so we could spend an afternoon chatting about other things and, interacting with our PhD students and some other junior faculty who are all like, Insper has a very strong evidence-based vein, and statistics is part of the agenda of all research in the school. So I think it would be a nice environment for you to share your experience.
That'd be fun. And thank you for inviting me to talk. That was nice.
Yeah. All right. I'm going to stop recording now.